All right, is the audio good?
It sounds good here.
Okay, great. Okay, everyone. So recently there was a year 2 review for the CHEETA project, which is a consortium between several different research institutions, including Illinois, to develop technologies for high efficiency electric aircraft. And as part of the annual review was the superconducting machine design of the proposed airplane, which is what the Heron group here is working on. So in today's presentation, I'll be taking us through all the work that's a summary of all the work that our team has done. Well, a summary of the at least the motor topology evaluation that our team has worked on over the past year. So here's the team. So we have most of the Heron group, along with Professor Banerjee and Shivang, and we're also working with some other research institutions. So just the general overview of the CHEETA project for those who don't know. So the CHEETA project is developing technologies for an airplane that we're proposing to use very cold cryogenic hydrogen fuel to power the airplane, and we'll have superconducting motors powering fans, which will be driving the airplane. So obviously developing superconducting motors of this magnitude is a huge research challenge, and it's a very new and exciting research challenge that our group is happy to take on. So there are a few key questions that we need to answer. So first of all, what's the most suitable machine topology? We do want to incorporate superconductors, but do we want partially superconducting, fully superconducting? With AC superconductors, there's also AC losses to take into consideration. So there's a lot to take into consideration. How does the system integration impact machine design and vice versa? So obviously the machine is not isolated. We also have to design it along with the propulsion system, the propulsors, and the rest of the power electronics, the cooling, which was my primary research focus, and the rest of the airplane. There needs to be an AC loss evaluation. This is something that hasn't been, there's not a whole lot of experience in. So we need to estimate the AC loss and evaluate the existing, the models that we have for estimating the AC losses. And finally, some bench tests to reduce the risk. So this includes experimental test of the AC losses, as well as testing superconducting winding and tests on the cooling of the superconductors. So here's an overview of the possible machine configurations that we could have gone with. So the 4 configurations that we looked at in these studies were a outer rotor fully superconducting machine, an inner rotor fully superconducting machine, as well as 2 partially superconducting machines. So one, a permanent magnet motor, where the field is created by permanent magnets at room temperature, and the armature windings are superconductors. And another partially superconducting, where both the field and armature windings are at 20 Kelvin, but only the field is superconducting. So I'll now go through the comparison of these topologies. So for the outer rotor motor topology, this is a basic diagram. So on the stator, we have MGB2 superconductors, the MG superconducting winding, and on the rotor we have also the superconductor winding for the field winding, and you'll also notice a third set of windings, which are the shield windings, and that's to contain the magnetic field of the rotor, and that's to avoid a bulky back iron in the motor. For an inner rotor fully superconducting motor, it's similar, but the field windings are on the inside with the armature windings on the outside. For a permanent magnet motor, the permanent magnets would be on the rotor and would be on the outside. So for a fully superconducting motor, shown here are the equations that are used to estimate the losses in the windings. So even though it's superconducting, there are still AC losses with AC currents. And this applies to the armature winding in the field windings in the rotor. You wouldn't have AC losses because the current would be direct currents. There would only be a very small parasitic heat losses. For a fully superconducting machine with a outer rotor, we conducted this study and produced this chart with possible designs. And shown here is a flux density diagram of a 2.65 kilowatt outer rotor design. And our study showed that a 8-pole motor was identified as having the best performance. So this was our selected baseline design. It was a fully superconducting outer rotor design. And on the right, you can see the coolant circuit design, which involves passing cold liquid hydrogen through helical stainless steel tubes, which removes the heat from which removes the AC losses from the armature windings. So for a fully superconducting machine for an inner rotor design, these were the studies that we conducted on an inner rotor design, and as you can see, the performance, the power density is pretty similar to the outer rotor design. So we concluded that even though for right now we're having the outer rotor design as our baseline, we're keeping the inner rotor option open if it turns out to be more convenient for something like cooling or for other considerations. So this is a study on an 8-pole fully superconducting machine, and so this is a this is a study of flux density versus total loss, and you can see that beyond around 0.7 Tesla flux density, the loss exceeds the allowable cooling budget that we have for the plane. And the cooling budget is determined by the amount of liquid hydrogen that's stored on board the plane. And likewise, we could also have a lower flux density design that makes it much easier to cool the motor, but it would be heavier. So it's a trade-off between weight and cooling capacity. And yeah, again, the inner rotor and outer rotor designs perform similarly. So now here's our study on a permanent motor with a superconducting armature design. So one of the advantages of this design is that there's no superconducting coils on the rotor. And why that's an advantage is because it can be tricky to cool rotating superconducting windings. It has been done at using liquid helium, but what's tricky about it is that there needs to be a rotating fluid coupling, and with liquid hydrogen, and liquid hydrogen can be very leaky, so a rotating fluid coupling can be very complicated and is not necessarily desirable. So with permanent magnets on the rotor, this eliminates the requirement to put cryogenic, to cool the rotating coils with cryogenic fluid. The disadvantage with the design was that it was much heavier. So ultimately, we decided that this design was not as good as the fully superconducting designs. And here's a more detailed comparison of the partially superconducting motor design versus the fully superconducting design. And as you can see, the magnet weight really contributes a lot to the total weight of the motor, and the power density for fully superconducting is about twice as much as for the partially superconducting. But it should still be noted that the partially superconducting, the power density is pretty good compared to conventional machines. But the fully superconducting machine is clearly better. Yeah, so again, the permanent magnet motor is heavier compared to the fully superconducting motor. So another alternative we used for, so the fourth motor topology that we explored, and the second partially superconducting topology was using an aluminum conductor instead of a MgB2 superconductor. And here are just some details of the aluminum conductor compared to the possible aluminum conductors compared to the MgB2 conductor that I discussed earlier. So in this design, we would have the aluminum conductor for the armature and field windings. So, and the advantage of this is that since the aluminum wouldn't be superconducting, there's no chance of a quench, and it can operate at higher temperatures in the expense of higher losses. And while there's no AC losses, or while there's no hysteresis loss and transport current loss, there are resistive losses since it wouldn't be superconducting. And another disadvantage is that they're currently not commercially available. So this is really only for a theoretical or a proposed aluminum conductor. So this is the selected design. This is the selected design that we looked at for the aluminum machine. And so some comparisons with the fully superconducting machine. The performance is pretty good, and the air gap flux density can go up to 1.2 Tesla. But again, it's using an aluminum conductor that currently isn't commercially available, whereas the MgB2 conductor is available. So just a summary from the generator topology study is that the practical design space for the air gap is between 0.4 and 0.7 Tesla. The inner rotor and outer rotor designs for the fully superconducting machines perform similarly. The cryo-cooled aluminum machine actually performs better than the fully superconducting machines, but the aluminum conductor has yet to be developed. And the permanent magnet motor with superconducting armature coils is heavier compared to the other topologies we looked at. So all the options are pretty promising, but right now we're looking at focusing on a fully superconducting machine with either an inner rotor or an outer rotor, depending on cooling requirements and other considerations. So that's it for the motor topology study, and I can take questions, or I could also present about some of the other experiments that we presented, which is a separate presentation, but it's also part of the review. But first, I'll take any questions about this presentation. Yep.
Can you go into what would be unique about this aluminum conductor? Is this just pure aluminum that has a different has a coefficient of temperature that allows it to get to low resistivity at low temperatures, or is there something unique about it?
So the aluminum, I believe it's ultra pure aluminum, so it's like 99.999% aluminum. So like at very low temperatures, the resistivity is very, very low, even though it's not superconducting. And that's really all I know about it. That might be a question for Deepan.
So the challenge is as much just getting that pure aluminum in the process and handling that type of aluminum.
Yeah. Oh, sorry. So the question was, what's the challenge about the aluminum conductor, and why isn't it commercially available?
Oh, yeah, I can answer this question. So, I mean, right now, earlier there was an interest on this high purity aluminum conductor. One of the technical difficulties is getting that high purity of aluminum, and also when you get this high purity aluminum, it's not very solid. It's more like it's not like a solid at that high purity. So what they do is they also need to make a metal matrix, and they have to insert this high purity aluminum inside it. So the reference I used here is that from 1991. So they made like 133 filaments, 0.79 OD, and like 20 micron filament diameter this conductor. So however, because of this OD is very high and the filament size is like twice of what we use for MgB2, the losses are significantly higher than the MgB2 conductor. But right now, we think that with the current technology, these conductors can be improved. So if we make the high purity aluminum conductor like MgB2, strands to that level with that much of twist pitch, then the losses would be very small. Even we in this presentation, what we saw that this performance would be even better than the MgB2 cable, because the major difference between the MgB2 and the high purity aluminum is that the high purity aluminum doesn't have a quench, and also we don't need to have a safety margin. So if the temperature goes up, resistivity goes up, the losses will go high, but it's not going to go quench and then increase the losses suddenly. So that's one of the reasons why the aluminum conductor is preferred. So does that answer your question?
Yeah, we're good.
Yep.
So lately in the news, the auto industry, there's been a lot of debate going on whether hydrogen will be life
sort of concern of similar, bypassing in the aircraft industry, or does it look very solidly that we will be using hydrogen in the near future before we transition to some other technology?
So this was talked about a little bit in, oh, sorry, the question was that in the auto industry sort of bypassed hydrogen fuel and went straight to electric vehicles. And is there a concern in the aircraft industry that the industry might just go straight to battery powered planes and not hydrogen? So this question was discussed a little bit in the review. And so currently, so one of the key differences is that for aviation, the infrastructure needed to distribute the hydrogen would be a lot less than for cars, and that currently the rate of like the rate of improvement of batteries is slow enough that it seems that going for a hydrogen powered plane would be a faster route to a zero emission plane than waiting for batteries to become light enough. Okay, so I guess Thanatheepan is on the call. Thanatheepan, do you want to present about the experiments?
Yeah, sure, I can go through it.
Okay, I can.
Do you want to navigate? Okay, good. Do you hear me? Is my voice clear?
Yes.
Okay. So as Josh mentioned that right now we are on the second year of the project, and we are looking at how to reduce some of the risk that associated with this hydrogen powered electric airplane, and specifically we are looking at how we can reduce risk associated with a fully superconducting machine. So it's a new technology, so we are looking at some of the bench tests that we can do to reduce some of the risk. So as Josh mentioned, that was the team. And here, so I'm looking at the fourth question. So we are looking at 3 to 4 experiments. One is that to validate the AC loss models, because fully superconducting machine, but because we are using as an armature winding, so we have these AC losses. So we are using some of the models derived from theory, but there's no data points available at the operating region of our fully superconducting machine. So we are looking at to validate these models at the operating condition. And we are also building fully armature winding. So we are partnering with Hypertech and Ohio State University to experimentally test the armature winding at the operating condition of the machine. And also the third one is we are looking at alternative cooling methods. So for example, right now with the hydrogen available in the plane, we can cool the armature winding that is stationary, but if we want to cool the field winding, which is rotating, we need to send this liquid hydrogen through a transfer coupling through the rotating parts. So which introduce some additional risk in the machine. So we are exploring some other methods to cool the rotating part of the machine. So as it mentioned earlier, we were looked at the permanent magnet, but those designs are heavier compared to fully superconducting machine. So like 5 times heavier than the fully superconducting machine. So if you look at only the active weight, but if you look at the total weight, it is almost twice heavier than the fully superconducting machine. So we were looking at some alternative cooling method using a rotating cryocooler machine setup. So we have a test bench to validate whether we can cool the rotating parts of the motor with the cooler, a cryocooler. Then also Josh is working with Wolfgang from GE to test on the two-phase cooling, and he will discuss that later. Let's go to the next slide. So so this is covering the detail of the 4 bench tests we are doing. So as I said, like we are looking at MgB2 armature winding. MgB2 is a superconductor. Then we were looking at different former, like for example, the Hypertech that who manufactured our winding. So they are they are the expert on making this winding, but however they are not expert on making armature winding. So they only make this winding with a steel coil, but we cannot use this steel coil former because of the AC, the eddy current losses would generate on the former. However, to do a first pass, because there are a lot of challenges associated with that, because once you made the winding, need to be handled very carefully. So we asked them to make the similar coil they made for in the past. So they made a steel coil former. But at UIUC, we are looking at like ceramic coil formers like boron nitride and aluminum nitride. So we made one coil former using boron nitride because boron nitride, there is no eddy current losses on the coil former. And also we are looking at whether we can completely remove the coil former from the winding. So we can, that would be the ideal solution for an armature winding. So we are looking at that too. So as I mentioned earlier, like we are looking at the rotating cryocooler setup to cool the rotor. And also we are setting an AC loss test setup to validate the model at the operating condition of the winding. Then we are looking at the two-phase cryogenic cooling. So if we go to the next one. So this is the FEA simulation of the winding. So as a armature winding itself, it generates like 0.2 Tesla. And if you look at the 3D, and it will generate at 0.23 Tesla, because in the end turns, the flux density is higher than the cross section. So we need to do a 3D solutions to look at what would the peak field at the end winding. Like at the machine level, what we have it is 0. Yeah, sure. I can share the screen as well. So Robin says that I need to share the screen. If I share the screen, can everybody see from in the room, Josh, or how does that works as well? Or I can change the slide, and you can also change your slide, right?
Sure. Why does he need to share the screen?
Because the other people in the Zoom cannot see the screen. Is that what? Yeah, that's what Robin's saying. But you are sharing, right? So everybody should be able to see it. I can see it. Should I also share? Do you see my presentation now?
I can see it now.
Do we need to do this way, or?
I can see it now.
Okay. So as I mentioned earlier, so this is the 2D and 3D analysis of the coil that that's go into the machine. So we looked at what would be the eddy current losses generated on the steel former. So our machine will be operated at 300 hertz. At 300 hertz, the eddy current losses on the coil former is huge. So we cannot use this steel former at our machine. So that's why I'm looking at the boron nitride coil former as well. So in the boron nitride coil former, the eddy current.
Yeah.
Oh, see, that's much better. We were showing the first half, we were just showing a picture of this screen.
Is there any questions for me? Okay, so I will continue. With the boron nitride coil form, as we mentioned earlier, there's no losses at all. So we are exploring whether we can use the boron nitride coil form as an armature winding. But still, it has some challenges because we are making it as a racetrack winding. So we are looking at how we can bend the end turn so we can use it as an armature winding. Here I have the picture of the coil former that manufactured in University of Illinois at our machine shop. So there's a lot of holes here that will help to do the VPA process, because once we wound on these windings, so after we need to go through the VPA process, so we need to make sure that there's no air bubbles trapped inside the winding, because if there's air bubble trap, then it may create hot spot and it will lead to a quench. So therefore, there are a lot of holes put on the windings, and also it reduces the eddy current losses on the coil former. Though this winding is not suitable for this 300 hertz machine, but if we are exploring whether we can use the steel former for a wind turbine application, because they are the frequencies like less than 1 hertz. Therefore, the losses on the steel former would be small. So this is the both pictures that we made. The both of these these coil formers are made in University of Illinois. The first one is the steel, and the second one is the boron nitride coil former. So the one that we made here is the scale is to 1 to 2, meaning that the original winding would be twice of this one that will go into the machine, but we made like half. And then when we make the boron nitride, we made it even smaller than that, because this one we used to retire most of the risk associated with making the winding, taking out the winding, doing the VPA process, testing, and all these things. If we validate all these problems, then it will give a confidence to make more windings that can be tested under the real condition. So here the pictures showing that this is removed all the components on the coil former. This one after adding the mica insulation on where the leads are connected, and this is the showing the different sensors that will go under the on the winding. So there are a lot of temperature sensors and current sensors installed on the winding to measure different values while different measurements while we are testing the winding. So the next few slides I will go through the winding process. So these pictures are sent by Hypertech to me, showing that how they are manufacturing the winding. So they put in the winding machine, and they first wound the superconducting cable on the winding. So this one is after the winding. This one is actually before the heat treatment, because after the heat treatment, the superconductor become very brittle, so you cannot bend the wires too much. So first they wound it, then they do the heat treatment here. They put in the oven, and then once they heat treat, then you have to handle the superconducting wire very carefully. So this is after the heat treatment. So then after that they attach the leads. So this is the copper leads that we will big copper lead used to transfer a lot of current to the wire. So we are pushing with this small wire. We are going to push more than hundreds in the order of 100 amps. So that's why there's a big current lead is installed on the winding. So once you connected the lead, heat treatment, this wind and heat treatment, connect the lead, then do the VPA process. So you see that there's a resin used to make sure that there's no air bubbles inside the winding, and then the winding has a good connection to the steel former. Therefore, we can cool down to 20 Kelvin. So do the vacuum impregnation process. That winding. So here it shows that during the process of vacuum impregnation, so you can see that the air bubbles coming out of these holes to those the pictures. Then we have the completed winding. So here after the potting process, this is the winding that, but this need to be cleaned and removed the excess resin on the outside. And then the winding is right now on Ohio State University to test under the operating condition. So this is the other experiment we are doing at here at University of Illinois. So here we are looking at whether we can cool the rotor windings as on the rotor without sending the hydrogen through the transfer coupling. So you can see that the cryocooler here is located in this part, and we have vacuum chamber here, and where we put the sample, HTS sample, and the whole the whole system is rotated by the drive. So with this rotating cryocooler, we cannot use MgB2 or low temperature superconductors. We need to use a high temperature superconductors because this cryocooler can cool down to 40 Kelvin. So that's why we are looking at this option. So if we replace the field winding, right now we at all our models we use MgB2 windings, but if we replace with HTS winding, then we can use this rotating cryocooler to cool down the winding. So here we have some initial result. So this is the performance of the cryocooler. So at 0 watt, it can go, I mean, if we don't cool the sample, then it can go up to 36 Kelvin. But at around, if we keep it at 50 Kelvin, it can lift 5 watt loss from the sample. So that's the target. So we wanted to, while we are rotating the cryocooler at 3,500 RPM, that's the targeted speed, and we should be able to keep the sample at less than 50 Kelvin. So that's the experiments that we are trying to do at ECE. So we did some initial experiment. So what it is show is the pressure drop on the chamber and then the temperature drop. So what we show with that, what we show here is that we first in the initial test we rotated the cryocooler and the sample to 350 RPM, and then we were able to keep the sample at 40 Kelvin while it is rotating. So it is a success, saying that we can use the cryocooler that we have in the lab in a real machine, but we should rotate up to 3,500 RPM to benchmark the result to see that it can operate at higher speed. So, however, we also observed that the huge vibration comes from the cryocooler. For example, here show that here that everything off, and then here the whole setup is running at 350 RPM. Then here we turn on the cryocooler. So you can see that once you turn on the cryocooler, there's a huge vibration coming. So this means that if we attach this winding, if we attach the cryocooler to the rotor, that this vibration will be translated to the field winding. So we can use some thermal straps to avoid that these vibration going to the winding, but this can be addressed when we go further on, like if we hit the 3,500 RPM, then we can further address this vibration and see that how we can avoid this one going to the actual field winding. So the third setup is that we were looking at experimentally validating these AC loss models that we used on our study. Right now, the data points available for this MGB2 cable is not available for a rotating field. For example, there are a lot of data available for a stationary field, but in the machines, the winding sees a rotating field. So here it shows that if you look at a one sample winding here and then armature winding, this is how the field is going to change for the winding. So it is a rotating, but also having harmonics in the field. So we need to simulate such a field inside this inside this chamber to see that how the losses are on the winding. For a start, what we are starting with is that we are trying to do a pure sinusoidal rotating field, and we are trying to measure the losses on the sample. So here what we are having is a permanent magnet attached to through a vacuum coupler, and then we can rotate this coupler up to 9,000 RPM. So that means can be translated to 160 Hertz because a two-pole permanent magnet rotor. And then we place the sample inside it to measure the losses on the sample. So here I have more of the picture of the permanent magnet right now being built. So here we have a 40 millimeter air gap, and then so we have a like more than 1 Tesla field. So and then we can place the sample inside it, and the whole the permanent rotor will rotate. So the samples will experience a rotating magnetic field, which is what the armature winding will see in the real machine. And then we would like to validate the loss models that we use to estimate and the losses on the fully superconducting machine that we designed for the CHEETA project. With that, I give it to Josh. He'll talk about the cooling.
Okay, so we're also planning an experiment to assess our models for determining for analyzing our cooling system in the motor. So in the top right here, you can see a CAD model of the cooling system. So like I said, the liquid hydrogen is piped through long helical stainless steel tubes where it removes the heat from the armature coils. On the left, you can also see a new design for those tubes, or for the channel for the liquid hydrogen that we've been looking at, that increases the surface area that the liquid hydrogen contacts. There's also, right now I'm working on a review paper of current epoxy technology. So, so currently it's not clear that, well, currently a big barrier to effectively cooling the motor is the epoxy that holds the superconducting wires together in the coil, because that doesn't have great heat conductivity. So we're looking at if there is epoxies that do exist that have better heat conductivity than the standard epoxy, or if anything new needs to be developed. And in the bottom right, those are some calculations we ran on the current cooling design that we have. So currently it can get it under 30 Kelvin. We'd ideally like it to be a little colder, so we're still working on optimizing the cooling design. So one of the problems with modeling a cooling design like that is that right now there's not really any experimental validation for two-phase flow boiling of cryogenic fluids in a looped tube. So so we're planning an experiment to examine the heat transfer of boiling cryogenic fluid in a looped tube. So our first experiment, we're starting out with liquid nitrogen because liquid hydrogen is a bit harder to handle. And then eventually, hopefully we would extrapolate that to liquid hydrogen. So the experiment we're planning is basically to pump liquid nitrogen first through a prep section where where it heats up the nitrogen to the desired vapor ratio, so ratio of vapor to liquid. And then there's a test section with measurements before and after. And the test section is where we would simulate the cooling that would go on in the motor by having a heater, and measure the fluid before and after to determine the heat transfer that took place. And so we would start out with a straight tube just to set a benchmark, and then test it with a looped tube. And with that, I'll pass it back to Thanatheepan.
Yeah, so this summarizes the presentation part 1 and part 2. So though we explored different motor topologies, so what we understood is that with the current technology and the technology readiness level, MGBT cable is the right candidate for the CHEETA project. So that's why we went ahead and made armature winding using MGBT cables. So some of these this conclusion is not relevant to this team. So, but because it's a collaborative effort with the other team, so we also shared the machine models and the ACLOS models, extended ACLOS models for the with include the harmonics present. So and then finally the other ones is that MGBT armature coils have been fabricated, and right now it's being tested at Ohio State University. So and we will visit there to do the experiments with them. And we also presented an alternative cooling method that will reduce the risk of hydrogen transfer coupling, because when you do the transfer coupling through a rotating parts, then there's a problem of hydrogen leaking, and there was some safety concern. So this rotating cryocooler will solve this problem. And the ACLOS models, so as I mentioned earlier, there's no like data points for especially for rotating field. So there's models available for a stationary field, and the multi-filament samples placed on them. There's no like experimental data up to like the operating condition around 0.5 Tesla and rotating field. So with that setup that we are doing here, we should be able to measure and validate the loss models. And the final thing is that at the second year, we have planned to finish some of these, but there's some delays happen on the fabrication, and so we hope to finish all these experiment test bench in the third year. So that's the plan.
Okay, so that concludes our presentation. So are there any questions on the second half of the presentation on the experiments? Okay, well, thank you for having us present, and
Thank you very much.
we hope you enjoyed the presentation.